Excellent, actually. So here we go. Logical English. So we just heard Thorne give a fairly technical presentation, which I would try to make a little bit more intuitive for those of you who are not familiar with logic programming in particular. So these are my two colleagues with whom I've worked quite closely and who are responsible for the implementation of what you're going to be shown today. There have been many other contributors to this work, some MSc students, some companies, some people at Stanford and at Confilo in Bologna. So what's the problem? Look at this. Here you go. You want to add to this list of yet more programming languages. And what we'll end up with, well, is what we already have. We have a mess, a computer science mess. Logical English aims to solve that problem by providing us with a single general purpose computer language, which can be understood without knowledge of computing, logic, or mathematics, and is inspired in large part by the language of well-written legal documents. Now, when I say general purpose computer language, I don't mean programming language, unfortunately. I mean database language, AI, knowledge representation language, specification language, what have you. So let's compare logical English with ordinary English. Here's a sentence. All meetings with unvaccinated people are prohibited unless they are excused. And the first thing you notice is this ambiguity with the word they. Does they refer to unvaccinated people or does it refer to all meetings? And how do we deal with this exception? All meetings are prohibited except for those meetings which are excused. It's been suggested logic programs are not very well suited for dealing with rules and exceptions, but our own experience is quite contrary to that. In logical English, we use logic programming form, and that logic programming form is a single conclusion. In this case, a meeting is prohibited, and a number of conditions. So there's an asymmetry between the conclusion, which is typically singular, and the conditions, which are typically multiple. So a meeting is prohibited, and that meeting, or rather the predicate, which is in the conclusion, consists of a constant part, prohibited. We call that the predicate. And its argument is a meeting. And that argument is variable. There could be different meetings. And so for variable arguments, we use the indefinite article a. And for later occurrences of that same variable, we use the definite article the. Very similar in some respects to what you find in programming language such as Prolog, because we have implicit variables rather than explicitly quantified variables. Notice that we don't have any plurals. We don't have any pronouns. Pronouns are a tremendous source of ambiguity. This word they is where the trouble started. And similarly, plurals tend to be a source of ambiguity as well. So we, wherever the plural is meant, we replace it by the singular because it has an even more precise meaning. And notice, as I mentioned before, that we can deal with exceptions, and the way we do so is non-monotonically by adding negative conditions. It's been suggested that we need a non-monotonic logic, and of course, logic programs, for those who have become more familiar with them, will know that logic programming is one very simple and very powerful way of dealing with non-monotonic reasoning. And notice how this all translates into, well, you can't, I don't know if you can see this, but it translates into Prolog in particular by having a single conclusion that something is prohibited if that something is attended by something else, and that something else is unvaccinated. And in this case, the meeting is not excused. A very important feature which is not widely recognized and which Thorne has drawn attention to, thankfully, is that we can embed predicates inside other predicates. And this can be regarded both as higher order programming or modal order logic for representing things like obligations, and or meta order for writing, for example, meta interpreters, which for compiling one for simulating one language by another. And here's an example of that. A person has an obligation that the person pays a fine if the person attends a meeting and the meeting is prohibited. The word "that" is the word the key word we use in order to link a meta predicate, in this case obligation, to a lower level object level predicate. And of course, this translates into programming languages, logic programming languages such as Prolog, by having the object level predicate embedded inside the meta level predicate. Well, the way we distinguish between predicates and arguments is done by templates, and this allows for very flexible forms of controlled natural language. So, for example, we indicate variables in the implementation I'm going to show you in a minute by surrounding them with asterisks. So an event is a variable, could be any event, could be this event, and we have the invariant part of the predicate, which is that the event is prohibited. I'm going to show you a few examples, one of which is historically interesting because it's the first application of Prolog to a very significant legal application, namely to the British Nationality Act, which describes when a person, any person, you or me, acquires British citizenship under various conditions. A person inputs a choice and an amount is an interesting application to the rock, paper, scissors example, often used in blockchain smart contract courses. And here we use a predicate called inputs and with three variable arguments: a person, because anybody could input, a choice could be rock, paper, scissors, and an amount, which is a gamble. Let's say I'll put in $1,000 if you put in $100. And notice that the word "and" can occur inside a predicate, and the fact that it's declared by a template means that it will not be confused with the "and," which combines several conditions into a rule. And here's a final example I would love to show you, which shows the general purpose nature of logical English, the definition of a set being a subset of another set. And here we distinguish the use of for variables from the use of as part of a predicate by simply not surrounding a subset here by asterisks. Well, let's immediately jump to an implementation which all of you can access, just like I'm accessing it now. This is the SWISH implementation, SWI Prolog, a wonderful system developed by Jan Weilemacher in Amsterdam. And if you go to the examples menu, you'll see that you have a Jupyter-style notebook, which is a description of how to use the language. You can express various scenarios. You can describe various templates. You can have rules in a knowledge base. You can, as I said, store queries, and then you can have stored queries. So here's an example in our little notebook here. Let's see how this works. Here we have some templates like the one I showed you before. A person acquires British citizenship on a date. And then we have the rule. Can you see this? Let's move it over if I can. Oh, come on. There you go. Here we have a rule in the knowledge base called citizenship, which has a single conclusion that a person, any person, you or me, acquires British citizenship on a date, any date. If the person is born in the United Kingdom on the date, so that's the same variable referred to a second time, and the date is after commencement, which is the 1st of October, 1984, and another person is the mother of the person, or the other person is the father of the person, and the other person is a British citizen, or the other person is settled in the United Kingdom on the date, which is the date that the person is born, and also the date on which the person acquires British citizenship. We can declare various scenarios and we can try them out. So here's a scenario Alice. Give it a name. In the scenario Alice is the mother of John. The fact that this is uppercase doesn't mean it's a variable, because in English we we don't represent variables by uppercase or lowercase as is done in Prolog. So we simply have a fact which says, or an assumption in the scenario Alice, that Alice is the mother of John. John is born on a particular date. That date is after commencement. And luckily, Alice is a British citizen. So suppose we now ask the question who, or which person rather. You see, we don't want to say who, what, where, when. We want to have a uniform standardized syntax. And that standardized syntax uses a single word which, in the same way that we use a standardized syntax for quantifying variables using a and the. So which person acquires British citizenship on which date? Now in the SWISH window over here, let's see if I can get access, if I can move over. Let's move over. Right. We can combine using, using the SWISH window, we can look at a number of, that's not the examples I want. Let's have a very simple example. Answer, let's answer Alice with, what was that? What was that knowledge base? What was that? Alice is a scenario and the query is 1. So it's answer 1 with Alice. Can you hear me, by the way? I don't hear any noises. I'm a bit nervous that nobody's listening to me. Well, we get an answer that John acquires citizenship on the date, which is the date of his birth, and in fact, at the beginning of the very day. If we now look for other answers, we are told that there are no further answers. We have other scenarios here, and all of which are very interesting. Where did they go? Oh, I'm sorry, I'm still in the notebook. No wonder it's not doing what I expected. Let's go out of this notebook and look at this. Now, here's the much more interesting citizenship example, which has a lot of other interesting examples in it. For example, suppose in scenario Harry, John is still born on this date, still after commencement, but this time we're interested in Harry, who is the father of John, and Harry is settled in the United Kingdom. Well, you can imagine John now obtains citizenship through the fact that his father is settled in the United Kingdom. But suppose we don't know for sure that John is the father, that Harry is the father of John, but rather Harry simply claims to be the father of John. And Harry is settled in the United Kingdom, and if you can believe Harry, then everything is going to work just fine. So let's try that and see what happens. So we're going to now, I want to hide that. We're now going to ask the question, we're now going to try scenario trust Harry. And we're going to use the query. Where is the query? The query which I've called British here. I called it 1 before in that notebook, so this is now slightly different. And I hit the run button, and I'm patiently waiting to see what happens. Patience is not my greatest virtue, but the answer is yes, John. But then the question that naturally arises is why? I want an explanation. So let's ask that same question using a prologue like we haven't yet gotten, not with trust Alice, because if Alice says that Harry is the father, it's not obvious whether you can trust her. But in the case of Harry, let's see what happens. So we run this. And we're now looking for the explanation for the answer that we had before. And we're trying to be patient, and you're trying to be patient. And the answer is yes, it is the case. John does indeed acquire citizenship. And it's because John is born in the UK on a date which is after commencement, and Harry is indeed the father. And why is that the case? Because Harry says he's the father. So, but what makes you believe that Harry is the father just because he says so? So let's click to look for more evidence of that. And if we click on that, we'll find the rule, which I didn't show you before, that a person is the father of a person if the first person claims to be the father of other person. And here you can see that logical English allows variables if you want to use them as such. Okay, so I think it's about time to leave. There are some lovely examples here that I'm afraid you're not going to see in this little talk. The rock, paper, scissors example, where scissors beats paper, paper beats rock, rock beats scissors, and you have a first player and a second player. And if what the first player plays beats what the second player has played, then the amount which is the prize is the sum of the two amounts that have been gambled. Otherwise, the game is a draw. So that's a lovely example I would have liked to show you. There are other much more interesting examples, but and one way to find out what they look like is to click on this plus. And clicking on the plus, you'll see perhaps the most interesting example of all, which is a very complex example involving complex temporal relationships. And also obligations and defaulting on obligations and curing a default of an obligation at different times. It's a lovely little example. And as I say, the way to find them is by clicking on this little plus. So clicking on the plus, we have that loan example, the citizenship example, another wonderful example, the sets example, where you can have what looks like the classic definition of subset. A set A is a subset of a set B. If A is a set, B is a set. And for all cases in which a thing belongs to a set, it is the case that the thing also belongs to the other set. And here we can have sets either represented by facts, two families, two sets, two people belonging to different or similar sets, or we can represent those sets by lists. And we can ask questions. So let's see I'll just finish by asking a question. Let's look for an answer of which sets are subsets with the lists example. So if I run this, run, and make the screen big, and wait. We get our first answer. Alice and Bob is a subset of Alice and Bob. Alice is a subset of Alice, Bob. Whoops. Alice is a subset of Alice. And that's it. Okay, I finished my talk. That's that. I'll just click along. I've shown you all these. And I just want to finish very, very quickly. What is the future like? Is the future going to be a future of special purpose, domain-specific computer languages? Understandable with special training in computer science, mathematics, or logic, alienated from the vast majority of ordinary people, just what we have today? Or is it going to be something different? One computer language for all applications, understandable without special training, inspired in part by the language of law, a future that you can sample by starting with logical English. Okay, that's it. Thank you. Are you there?
Thanks, Bob. Very inspiring talk. We have two questions online. The first one is about the limitations of logical English.
You're asking, are there any limitations of logical English? Yes.
You should see it on your screen. The question should be displayed on your screen. It says, have you found any limitations for logical English, such as statutes that you could not encode? If yes, what were the features that logical English could not handle?
So far we haven't found anything that's caused difficulty, except that the English itself in many cases is much more confused than you might think at first glance. But in fact, although logical English is designed to be easy to read, it's not easy to write. I mean, to write ordinary English well is very difficult, but to write logical English is still more difficult and will require quite a bit of training. So although I say no training needed to read, a lot of training needed to write. It requires training to be logical, I'm afraid. Not everybody is logical, and that's one of the things that's necessary for using logical English. Yep.
All right, 2 more questions before we move on to the next talk. One in the room from Jimmy.
Hi. How would you imagine types to be included in this at all? Like if
Great.
you have types for atoms, like say rock is, is something in a like RPS game, Alice is a person. So like there could be a difference of rock beats paper versus Alice beats Bob, that sort of thing.
Well, you're absolutely right. The one feature which we haven't yet implemented, and we're not entirely sure about how best to do so, is the treatment of types. Prolog, in particular, is an untyped language, and what looks like types. When I say a person or an event, and these are that I could have replaced a person by a dog, and it would have just worked just as well because the types have no significance. So indeed, the next major step in the development of the logical English you've seen will be the proper treatment of types, and any advice about that would be greatly welcomed. I'm thinking mainly in terms of static type checking to check that all the types are compatible, but I'm also wondering whether runtime, reasoning time checking of types is also necessary. That's something I haven't entirely figured out.
Okay, one last question. Thanks. One last question that's been quite upvoted before we move on to the next talk. How does logical English deal or could deal with nullification amendment or other exogenous contractual normative changes?
Well, just like any other updates, I suppose. I mean, how does any language deal with a change of belief? You tell me how to do it and we'll do it. I mean, it's not something that is part of the definition of the language. It's something that has to do with the management of the language. And we haven't given any attention to that at the moment because it hasn't been an issue up until now. We're still working on quite a few examples, but that hasn't. We have to walk before we start running, otherwise we'll trip up.
All right, well, let's thank